Welcome! Today, we're diving into the fascinating world of quantum computing. You might have heard the term before, but what does it really mean? Quantum computing is a revolutionary approach to computation that leverages the strange and powerful principles of quantum mechanics. Unlike traditional computers, which use bits to process information as zeros or ones, quantum computers use quantum bits, or qubits, which can exist in multiple states at once. This opens up possibilities for solving problems that are currently impossible or would take traditional computers thousands of years to crack. Let's start our journey by understanding the basics. To appreciate quantum computing, it helps to compare it with classical computing. Classical computers process information using bits, which are like tiny switches that can be either on or off, representing a 1 or a 0. Every app you use, every website you visit, is powered by billions of these bits working together. Quantum computers, on the other hand, use qubits. Qubits can be both 0 and 1 at the same time, thanks to a property called superposition. This fundamental difference allows quantum computers to process information in ways that classical computers simply can't. So, what exactly is a qubit? A qubit, or quantum bit, is the basic unit of quantum information. Unlike a classical bit, which can only be in one state at a time, a qubit can exist in a superposition of both 0 and 1. This means it can represent both values simultaneously, vastly increasing the computing power available for certain tasks. Qubits are typically created using tiny particles like electrons or photons, whose quantum properties can be controlled and measured. Understanding qubits is key to grasping the power of quantum computing. Superposition is one of the most mind-bending concepts in quantum mechanics. Imagine flipping a coin. In the classical world, it's either heads or tails. But in the quantum world, until you look, it's both at the same time. Qubits can exist in a blend of 0 and 1, and only when you measure them do they settle into one state. This ability to be in multiple states simultaneously is what gives quantum computers their incredible parallel processing power. Another key concept is entanglement. When two qubits become entangled, their states are linked no matter how far apart they are. Changing the state of one instantly affects the other. This phenomenon, which Einstein famously called spooky action at a distance, is harnessed in quantum computing to create powerful correlations between qubits, enabling complex computations that are impossible for classical computers. Qubits can be created in several ways, using different physical systems. Some quantum computers use superconducting circuits cooled to near absolute zero, while others trap ions or photons. Each method has its own advantages and challenges, but they all rely on the delicate control of quantum states. Building and maintaining qubits is one of the biggest technical challenges in quantum computing today. Just as classical computers use logic gates to process bits, quantum computers use quantum gates to manipulate qubits. These gates perform operations like flipping a qubit state or creating entanglement between two qubits. Quantum gates are the fundamental building blocks of quantum algorithms, allowing us to perform complex calculations by controlling the behavior of qubits. Quantum circuits are sequences of quantum gates applied to qubits. By arranging gates in different patterns, we can create algorithms that solve specific problems. Designing quantum circuits requires a deep understanding of both quantum mechanics and computer science, as even small changes can have big effects on the outcome. One of the most exciting aspects of quantum computing is its potential for speed up. Certain problems, like factoring large numbers or searching databases, can be solved exponentially faster on a quantum computer than on a classical one. This quantum speedup could revolutionize fields like cryptography, optimization, and drug discovery. A famous example of quantum speedup is Shor's algorithm, which can factor large numbers much faster than the best-known classical algorithms. This has huge implications for encryption, as many security systems rely on the difficulty of factoring. Quantum computers running Shor's algorithm could potentially break current cryptographic codes, prompting the search for new, quantum-resistant encryption methods. Another important quantum algorithm is Grover's algorithm, which speeds up searching through unsorted data. While classical computers need to check each item one by one, Grover's algorithm can find the answer in far fewer steps. This could have applications in database, search, optimization, and even artificial intelligence. Quantum supremacy is the point at which a quantum computer can solve a problem that is practically impossible for a classical computer. In 2019, Google claimed to achieve this milestone by performing a specific calculation in seconds that would take a supercomputer thousands of years. While the practical impact is still limited, it marks a significant step forward in the field. Despite its promise, quantum computing faces major challenges. One of the biggest is decoherence, the tendency for qubits to lose their quantum state due to interference from their environment. This makes it difficult to maintain and manipulate qubits long enough to perform useful calculations. Overcoming decoherence is a central focus of quantum research. To combat decoherence and other errors, scientists have developed quantum error correction techniques. These methods use extra qubits to detect and correct mistakes without destroying the quantum information. Error correction is essential for building reliable, large-scale quantum computers, but it also adds complexity to their design. Quantum computers can be built using various physical systems. Superconducting qubits, trapped ions, and photonic qubits are some of the leading approaches. Each has unique strengths and weaknesses, and researchers are still exploring which technology will ultimately prove most practical for large-scale quantum computing. Superconducting qubits are made from tiny circuits cooled to near absolute zero, where they exhibit quantum behavior. Companies like IBM and Google use this technology in their quantum processors. Superconducting qubits are relatively easy to manufacture using existing chip technology, but they require extremely cold environments to function. Trapped ion quantum computers use individual atoms suspended in electromagnetic fields as qubits. Lasers are used to manipulate and read out their quantum states. This approach offers high precision and long coherence times, but scaling up to large numbers of qubits is technically challenging. Photonic quantum computers use particles of light, or photons, as qubits. Photons are less susceptible to decoherence and can travel long distances, making them ideal for quantum communication. However, controlling and interacting photons for computation is a significant technical hurdle. Quantum annealing is a special type of quantum computing used for optimization problems. Companies like D-Wave have built machines that use this approach to find solutions to complex problems by exploiting quantum tunneling. While not as general purpose as gate-based quantum computers, quantum annealers are already being used in research and industry. Quantum computing isn't just about faster calculations. Quantum communication uses the principles of quantum mechanics to transmit information securely. Quantum key distribution, for example, allows two parties to share a secret key with security guaranteed by the laws of physics, not just mathematics. The idea of a quantum internet is gaining traction. By linking quantum computers and devices through quantum communication channels, we could create networks that are fundamentally secure and capable of new types of information processing. While still in its early stages, the quantum internet could transform how we share and protect data. Quantum cryptography leverages quantum mechanics to create secure communication systems. Unlike classical cryptography, which can be broken with enough computing power, quantum cryptography is secure against any attack, as any attempt to eavesdrop changes the quantum state and can be detected. Quantum technology isn't limited to computing and communication. Quantum sensors use quantum effects to achieve unprecedented sensitivity in measuring things like time, gravity, and magnetic fields. These sensors could revolutionize navigation, medical imaging, and scientific research. Quantum machine learning combines quantum computing with artificial intelligence. By harnessing the power of qubits, quantum computers could process and analyze massive datasets much faster than classical computers, potentially leading to breakthroughs in pattern recognition, optimization, and more. Quantum computers are particularly well suited for simulating molecules and chemical reactions, a task that is extremely challenging for classical computers. Quantum chemistry could lead to new materials, drugs, and energy solutions by allowing scientists to model complex systems at the quantum level. Optimization problems, like finding the best route for deliveries or the most efficient use of resources, are everywhere. Quantum computers can tackle these problems more efficiently by exploring many possibilities at once, potentially saving time and money in industries from logistics to finance. Quantum simulation is another powerful application. By simulating quantum systems directly, quantum computers can help us understand phenomena like superconductivity, magnetism, and even the behavior of black holes. This could unlock new discoveries in physics and materials science. To program quantum computers, new languages and tools have been developed. Qiskit, Cirq, and QNumber are some of the popular quantum programming languages. These tools allow researchers and developers to write and test quantum algorithms, bringing quantum computing closer to practical use. Many companies now offer access to quantum computers via the cloud. This means researchers, students, and businesses can experiment with quantum algorithms without needing their own hardware. Cloud quantum computing is accelerating the pace of discovery and making quantum technology more accessible. A vibrant ecosystem of startups is driving innovation in quantum computing. These companies are developing new hardware, software, and applications, pushing the boundaries of what's possible. The quantum startup scene is attracting investment and talent from around the world. Big tech companies like IBM, Google, Microsoft, and Intel are investing heavily in quantum computing research. Their efforts are complemented by academic institutions and government labs, all working together to advance the field. Collaboration is key to overcoming the technical challenges ahead. As quantum computing grows, so does the need for a skilled workforce. Universities are launching quantum programs, and companies are training employees in quantum skills. The next generation of scientists, engineers, and developers will shape the future of this exciting field. With great power comes great responsibility. Quantum computing raises important ethical questions, from the impact on privacy and security to the potential for new forms of inequality. As the technology develops, it's crucial to consider its broader implications for society. Quantum computing and artificial intelligence are two of the most transformative technologies of our time. Together, they could unlock new capabilities in data analysis, optimization, and decision-making, leading to smarter systems and deeper insights. While quantum computing is still in its early days, its impact could eventually touch many aspects of daily life. From more secure communications to faster drug discovery and smarter logistics, quantum technology has the potential to transform industries and improve lives. Despite rapid progress, quantum computing faces significant hurdles. Technical challenges like error correction, scalability, and stability must be overcome. There are also questions about cost, accessibility, and integration with existing technologies. The road ahead is long, but the potential rewards are immense. Researchers have outlined a roadmap for quantum computing, with milestones like increasing qubit counts, improving error rates, and developing practical applications. Each step brings us closer to realizing the full potential of quantum technology. Education is key to the future of quantum computing. Online courses, workshops, and degree programs are making quantum concepts accessible to more people. As more students learn about quantum mechanics and computing, the field will continue to grow and innovate. Quantum computing is a rapidly evolving field. Researchers are exploring new materials, architectures, and algorithms. Breakthroughs in one area can have ripple effects across the entire field, making it an exciting time for scientists and engineers. Both hardware and software are critical to quantum computing success. Advances in hardware make it possible to build more powerful and reliable quantum machines, while software innovations unlock new algorithms and applications. The interplay between the two will shape the future of the field. Cloud-based quantum services are making it easier for businesses and researchers to experiment with quantum computing. Providers offer access to real quantum hardware and simulators, enabling users to run experiments and develop new algorithms from anywhere in the world. Quantum computing will have a profound impact on cybersecurity. While it threatens current encryption methods, it also offers new ways to secure data using quantum principles. Preparing for the quantum era means developing quantum-resistant algorithms and protocols. There are many myths about quantum computing. Some believe it will instantly solve all problems, while others think it's pure science fiction. The reality is more nuanced. Quantum computers excel at certain tasks, but are not a replacement for classical computers. Understanding their strengths and limitations is essential. The future of quantum computing is bright and full of possibilities. As technology advances, we'll see new applications, industries, and opportunities emerge. Quantum computing is set to become a cornerstone of innovation in the 21st century, reshaping how we solve problems and understand the universe. In summary, quantum computing is a groundbreaking technology that harnesses the principles of quantum mechanics to solve problems beyond the reach of classical computers. While there are still many challenges to overcome, the progress so far is remarkable. As research continues and more people get involved, quantum computing will move from the lab to the real world, transforming industries and opening up new frontiers of knowledge.